Okay, good afternoon, everyone. In today's lecture, we will continue what we have started in last lecture. In last lecture, we derived the standing wave function due to the interference of an incident wave and a reflected wave. And we have seen that the function was the product of two functions. One of them is a space dependent, and the second one, the cosine, is a time dependent function. In today's lecture, we will continue looking into the standing wave function and studying and understanding some of the distinguished points that we have in the standing wave function. We will also study the resonance and understand what does a resonance mean and how is the resonance being looked at when it comes to fundamental frequencies and other harmonics. So we will start first with the standing wave function that we have seen. And if you recall, we said that this function is a sine function multiplied by a cosine function that is a time dependent, causing the cosine to vary between 1 and -1, and that's what caused this sine function to oscillate between positive peaks and the negative valleys. So the cosine function is the one that is responsible for this oscillation that we have seen on the sine function. So today we will be looking at those distinguished points that we have in the standing wave. We will start with the nodes. Nodes, those are points along the medium of the propagation where we have the standing waves that have zero displacement. Those nodes, they are caused by the destructive interference between the incident and reflected wave. So those nodes, as I said, they have zero displacement. And if I am to refer to them here, this is at one time moment where we have maximum peaks and minimum peaks here. Those are the nodes. Those nodes will have zero displacement all time. The function is going to oscillate. The sine function is going to oscillate between maximum and minimum. However, those points, the nodes, will always have zero displacement. So if I am to look at another moment, let's see this one, then those nodes are here. And as you can see, in all moments that on all 4 or 5 snapshots that we have here, those nodes are always zero. So even here, the whole function is zero because we're multiplying by sine a phase of 90 degrees or 3 pi over 2. So in this case, all of them are zero. And again, the signs start to flip. The positive becomes negative and the negative becomes positive. However, those nodes will continue to be zero. So those are the nodes, zero displacement. Now, how did we calculate those locations? We have seen those locations graphically here on this standing wave function. But what about mathematically? We can calculate those locations mathematically by solving for the sine function. solving this for the sine function to be 0, because those displacements are always 0, which means if I solve for the phases that gives me the sine function to be 0, those would be the locations where I have the nodes. So I need to solve for sine kx to be 0 out of this function. So how do I do this? Now my function, that is a function of space and time, is minus 2a sine kx cosine omega t. Notice that the sine is a space dependent, while the cosine is a time dependent function. So for me, in order to solve for the 0 displacement, which means when sine kx equals to 0, definitely the function itself becomes 0. So I need to find the phase that will give me the sine to be 0. So if I am to draw the unit circle here, then I know sine theta in general is 0 when theta is 0 or pi. Is that right? Sine theta equals to 0. This means theta is either 0 or pi. So let me start with 0. This is theta equals to 0. And this is theta equals to pi. In both phases, I have sine to be 0. Fine. So this is only for those two phases. But if I am now to evaluate along the medium of propagation, I have more than 2 points. It's a periodic function. It's a periodic function that is repeating itself, which means the sine would be 0 when theta is 0, or when theta is pi, or when theta is 2 pi. So 0 or pi, add pi to it becomes 2 pi, which is here. Add pi to it becomes here, which is a function, a periodic function, that its period is pi. A sine function to be 0 is a periodic function with the period to be pi. Why? Because every incremental of pi, the sine would be 0. So this happens at 0, the sine is 0. Add to it a pi, the sine is 0. Add to it a pi, becomes 2 pi, the sine is 0. Add to it a pi, becomes a 3 pi, 4 pi, 5 pi, 6 pi. All those phases, the sine would be 0. So now I can describe this answer with the following. I can say theta is 0 plus m pi, such that m takes 0, 1, 2, 3, 4, 5. As far the medium propagation takes. Right? This is the solution that gives a sine to be 0. Fine. So what is this theta? If I am here looking at sine theta, and my function is sine kx, this means the kx is the theta. Kx is the phase. Okay, so now I can write the following. I can write that the sine Kx is 0 when Kx equals to 0 plus m pi such that m is 0, 1, 2, 3, 4, and so on. Now let me extend this, taking few of those phases. Then it would be Kx equals to 0, comma, that's the first one. The second one would be m1 pi. The next one would be 0 plus 2. I'm substituting m here with 1, m here with 2, and so on. So this is 3, 4, 5. If I divide by k, then I'll be solving for x, which is the location of those nodes. Then x equals to 0, pi over k, 2 pi over k, 3 pi over k, 4 pi over k. K is 2 pi over lambda. Then x is 0, pi over 2, pi over 2 pi over lambda, 2 pi over 2 pi over lambda, 3 pi over 2 pi over lambda, and then 4 pi over 2 pi over lambda. Now, if I cancel the pi, I will get x equals 2, 0, pi with pi, lambda over 2, lambda, 3, lambda over 2, 4, lambda over 2, which is 2, lambda, and so on. It's a periodic function. We found it in terms of the lambda because at the end, my lambda is the physical distance. It's not a physical distance, it is the length of the wavelength. So I'm writing it in terms of the length of my wavelength. So the nodes are 0, lambda over 2, lambda, 0, lambda over 2, which is this point, lambda, 3 lambda over 2, 2 lambda. Notice that the separation between two nodes is lambda over 2. So this one is lambda over 2, lambda over 2, lambda over 2, lambda over 2. Starting from 0 and going in intervals of lambda over 2. Those are the nodes. Those are where the displacement is always 0 in the standing wave. Any question about how did we calculate those nodes? Okay. So the next distinguished nodes, the distinguished points we have are the antinodes. Those points along the wave propagation where the displacement is maximum or minimum. along the medium of the standing wave. So here, if we have a strength, then those points are on the strength such that they are at the maximum point, at the maximum amplitude, and at the minimum. So those are those points. Those are the antinodes. And those points are caused by the constructive interference between the incident wave and the reflected wave. So due to the multiplication with the cosine function, that is cosine omega t, you can notice that the amplitude is being affected because this cosine function, as I said, varies between 1 to -1. So the peaks or the amplitude, those points are going to vary between maximum and minimum always. Till they get the point where all 0, and then they flip, and the sign, the positive became negative, and the negative positive, and then they go to the other extreme. The minimum becomes the maximum, and the maximum becomes the minimum. So how can we calculate or find those points mathematically? Back to here, it is important to understand what kind of function we are dealing with. We're dealing with the sine function. This time we will be solving for the sine function, but not to be 0, to be +1 and -1. So in this case, I would be solving for sine kx to be +-1. So what are the phases that will result into a sine to be +-1? We'll go back to the unity circle here. And we need to find out where are those phases. When theta is pi/2, I have the sine to be maximum 1. When theta is 3pi/2, I have the sine to be -1. So those are the points that my function is going to jump between. If the phase is pi/2, then the sine would be 1. If the phase is 3pi/2, then the sine would be -1. So notice that I have the same interval, phase interval, which is pi. The only difference between the antinodes and the nodes is the starting phase. In the nodes, I'm starting from 0, and then I'm going pi, 2 pi, 3 pi. For the antinodes, I'm starting from pi/2, and then I'm adding pi to it. Becomes 3 pi/2. Then add pi to it, becomes 5 pi/2, and so on. So in order to solve for my sine theta to be +-1, then this theta has to be pi/2 plus m pi, where m takes 0, 1, 2, 3, 4, and so on. It depends on how long is this string, or how long is this medium that my standing wave is constructed in. So those are the phases that will give me sine to be 1 minus 1, 1 minus 1. It's a periodic function with a phase interval of pi. But the starting point here is pi over 2, not 0. So I'm starting from here and then jumping to here, then coming back to here, then coming back to jumping to here by adding the phase interval of pi. So if I am to find now the solution again, since theta is kx, theta is kx, kx is the phase, then the solution would be kx equals 2 pi over 2 plus m pi, such that m takes 0, 1, 2, 3, 4. Now, if I am to extend this, then kx as the first one, when m is 0, it is pi over 2. The next one, when m is 1, it becomes pi over 2 plus pi. The one after becomes pi over 2 plus 2 pi. Pi over 2 plus 3 pi. Pi over 2 plus 4 pi, and so on. Now this is kx equals 2 pi over 2, 3 pi over 2, 5 pi over 2, 7 pi over 2, divide by k, pi over 2k, 3 pi over 2k, 5 pi over 2k, 7 pi over 2k. We know k equals to 2 pi over lambda, so we're going to solve it in terms of lambda again. Then x equals to pi over 2 times 2 pi over lambda, 3 pi over 2 times 2 pi over lambda, 5 pi over 2 times 2 pi over lambda, 7 pi over 2, 2 pi over lambda. Then pi with pi. Now in terms of lambda, this is going to be, the first one is going to be lambda over 4. The next one would be 3 lambda over 4. 5 lambda over 4. 7 lambda over 4. Now, the starting point is different. The starting point is here at lambda over 4. And then you add lambda over 2. The difference between the antinodes is the same as the nodes in the space domain. It is lambda over 2. Although the starting point is different, but the spatial difference is lambda over 2. So here, from here, lambda over 2. Lambda over 2. Notice I'm taking the spatial difference between the antinodes. lambda over 2. The starting point is lambda over 4, but the differences are the same, lambda over 2. If you look at the nodes, the starting point is 0, and the differences are also lambda over 2. So always keep in mind that the spatial difference between two nodes or two antinodes is the same, lambda over 2. The only difference here is the starting point. The node is starting from 0. The antinode is shifted, starting at lambda over 4. Is that clear? Any question about the nodes and antinodes in our standing wave function? Questions? Now let's introduce the resonance, which is the last part in our lecture. So the resonance is the natural oscillation of an object caused by an input force, such that the amplitude achieved is the maximum. The first frequency, the first resonant frequency, we call it the fundamental frequency. And then the upper frequency that are derived from the fundamental are called harmonics. Those harmonics are also resonant frequency at higher modes. Now, every object has its own resonant frequency or resonance. For example, this pen, if I excite it by hitting it, it will resonate. Maybe you don't feel the resonance here because I'm holding it. The resonance is being attenuated. But if you create the conditions that will amplify or let this object resonate, it will resonate. Every object has its own resonance. The resonance depends on the shape, depends on the material, but the resonance do exist for every object. To understand this, let's look at this example where we have a string fixed from both sides. You can look at the guitar. The guitar is an example of those strings being tightened up and resonating once you touch them. When you touch them, you are introducing an input force. You're exciting that string, and that's why it vibrates at the frequency of interest. And when you do the calibration, basically what you're doing is you're changing the tension such that you achieve the resonance frequency that you want for the sound that you want. So if we have a string that is fixed from both sides, and this string has been excited to resonate, we're going to see different resonance. If we have one antinode here, then we are talking about the fundamental frequency. So this is the fundamental frequency. This is the lowest frequency that has the longest wavelength. So one antinode, this means n equals to 1. And also means that this is the fundamental frequency of the resonant frequencies. So we have here two nodes at the fixed sides, and we have only one antinode. Now, what is the equation that defines the wavelength in terms of this physical length of that string? So if L is the physical length of the string, then how much is the wavelength for that fundamental frequency? The expression is the following. Lambda n equals 2 over n L. This is the wavelength in terms of the physical length of the string. So as I said, if you have one antinode, this means this is the fundamental frequency. This is the n equals to 1. So if you want to calculate the wavelength for the fundamental frequency, then you substitute n with 1, and then lambda 1 would be 2L. This agrees with what we have discovered earlier. Notice that the difference between those two nodes is lambda over 2, right? The spatial difference between those two nodes, node number 1, node number 2, is lambda over 2. Why? Because this is L, and in this case, L equals to lambda 1 over 2. Fine. If I have two antinodes, what does this mean? What's this pattern? Well, then this is the resonance of the second harmonic, because it has two antinodes. The second harmonic is a higher frequency. As you can see here, it will be double the frequency of the fundamental, which means if the frequency is doubled, this means the wavelength would be half, right? So here, if I am to calculate the wavelength for this resonance, which is the second harmonic, so it would be lambda 2, substituting n with 2, equals to 2 over 2L, which means lambda 2 equals to L. Notice that the wavelength for the second harmonic is half, the wavelength of the fundamental frequency. The frequency would be doubled. What about this? N equals to 3. N equals to 3. This means this is the third harmonic. It is also corresponding to 3 antinodes. So we have 3 antinodes. This means that's the third harmonic. So when you calculate the wavelength, you substitute n with the 3. So if you do so, lambda 3 would be 2 over 3L. That's the third harmonic. Right? Notice that the wavelength for the third harmonic is 1/3 of the wavelength of the fundamental, which means the frequency here would be 3 times the frequency of the fundamental. Is this clear? Any questions so far? Questions? So we count the antinodes to know what kind of frequency, what kind of resonance we have. If it's one antinode, then that's the fundamental. If there are 2 antinodes, then this is the second harmonic. If there are 3 antinodes, then that's the third harmonic. Now you can calculate the frequency from the wave speed, right? The speed here is given by this function. V equals to lambda f. If you have the velocity and you have the wavelength, then if you have the wave velocity and you have the wavelength, then you can calculate the frequency. And this is the expression for the frequency. In terms of the wave velocity, the physical length of the string, and knowing what kind of resonance you have, fundamental, second harmonic, third harmonic, fourth harmonic, fifth harmonic. So it's a function of the frequency, resonance, the physical length of the string, and the wave velocity in the string. Is this clear? So let's do this example. In this example, we have a 50 centimeter long oscillating string. This string establishes the standing wave shown below. The 5 waves shown are snapshots of the string taken at 0.012 second intervals. So the time interval is 0.012 second between those 5 functions of the standing wave. The displacements observed at 1 and 5 are the maximum displacements of the string. Understood? Now the question is asking us to find the period, find the frequency, find the wavelength of the traveling waves in this string. So, how can we find the period? What's given to me is the time interval, which is 0.012 seconds. The time between function 1 to function 2 is 0.012. The time between function 2 to function 3 is 0.012 seconds. The time interval is fixed, the same. Do you know how we can calculate the period? Any idea how to calculate the period? I'll remind you with the definition of the period. It is the time it takes for one complete oscillation to happen. So one complete oscillation, the time for one complete oscillation is the period. Would you be able to find the period from knowing the time interval for those between those functions? So let me help you here. See, the point P is at the peak, right? In order to calculate the period, you need to calculate the time this point P is going to take to go all the way down and come back to the same position. Does this help? Okay. So in order to calculate the period, you need to calculate the time this P is going to take to go to here, and here, and here, and here, and then come back. This completes one full cycle. So the period is 0.12. This is one time interval. How many time intervals I have here to complete one full cycle? 0.09, 0.096. I need 8 time intervals to complete one full cycle, right? This point P has to go all the way. So function 1 to become 2, become 3, 4, 5, and then back again to 1 to complete one full cycle. So the period in this case eight times 0.012 t equals to 0.096 seconds. That's the period. What's the frequency? Inverse of the period, right? So the frequency is 10.4 hertz. Next is the wavelength. Let me put the expression first. 2 over n L. The length of the string is 50 centimeters, which is 0.5 meters. Then what about n? How much is n? Could you tell how much is n? 2. Why 2? 2 antinodes. So 1, 2. I have 2 antinodes here. So I will substitute n with 2. 2 over 2 times 0.5, and lambda for the second, I don't know, okay. Probably you all know now, as 0.5 meter. B, what kind of harmonic is this? What kind of harmonic? What order? That's second harmonic, because n equals to 2. So this is second harmonic. Now the last one is, what is the speed of the traveling waves on the string? What is the speed of the traveling wave? V equals to F lambda. We know the frequency, which is 10.4. We know lambda, which is 0.5. Then V is 5.2 meters per second. So this is the end of our example. And this concludes our lecture. Unless you have questions. If you have a question, please ask before we end our lecture. Questions? Questions about the waves or nodes, antinodes, or resonance? No questions? Yes, go ahead. We're starting from pi over 2. Plus pi, it's going to be 3 pi over 2. Plus pi, it's going to be 5 pi over 2, and so on. No. Pi will give you sign to be 0. That will be nodes. Here, we're looking for the antinodes, which have a sign to be +1 or -1. Okay. Okay. Any other questions? No further questions? Okay. So in this case, we will end our lecture.